Welcome to section 3.1 polynomials video. This is my fifth attempt at this video, and it's a little bit lower tech because I just need now for everything to work well. So thank you for your patience for those that have been waiting. My Monday, Wednesday class, you should know that we've gone over some of this in class already. My Tuesday, Thursday class, you have to watch the entire video. The expectation is that you're watching that you're taking notes while you watch the video. That's what I'm going to be looking for in class as demonstration of having watched the video. Does it mean I expect you to learn all of this from the video? No, but we need to make sure that we have all of this in our toolbox as we move forward. So get as much as you can and make sure that any questions that you have about the material, you're writing it down somewhere. So to begin with polynomials, I'm going to talk about some of the vocabulary that are specific to polynomials. First, I have an example polynomial f of x here at the bottom of the page in the box, and some features of all polynomials. All polynomials have a variable raised to an exponent, and the exponent has a number in it. And a specific number is it's not negative or non-negatives. Meaning I can use 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but I can't use 1/3 or -4 or any of the numbers on the other side of the number line. So the next piece that I need to tell you is that the word coefficient are the numbers in front of the variable. Like -8 is a coefficient, 6 is a coefficient, -1/3 is a coefficient, 4 is a coefficient, -3 is a coefficient, and the last coefficient there is 1, and you may not have seen this, but that's attached to the x to the 0 term. And don't forget that x to the 0 is 1, so basically I'm taking -1 and I'm multiplying it by +1, which really doesn't do anything to it. So, having said that, the number with the highest exponent and the variable itself is called the leading term. The leading term is the first term you write on the other side of the equal sign if you're in standard form. Standard form is in descending exponent order. So if you'll take a look at the one we have here, the largest exponent here is 10, and that's why it's written first, and then follow 7, 6, 4, 1, and 0. So they literally are written in order of descent by their exponents. I'm going to erase this so we can see it a little bit more. The next thing I need to talk about is the leading coefficient. And this is important as we go on because the leading coefficient is going to tell us what the ultimate shape is of the graph. Is it going to follow the parabola or is it going to be a chair? And we're going to talk a little bit more about that later. The degree of the entire polynomial is the value of its highest exponent. So this particular polynomial here is a 10th degree polynomial, and it has 1, 2, 3, 4, 5, 6 terms. We say that with 6 terms. So if we're going to get really technical, this is a 10th degree polynomial with 6 terms. And I'll start erasing some stuff. We usually refer to any number that doesn't have an obvious x on it, the constant. So I think you guys have heard that one before. So the last thing I need to talk about is you already know some polynomials, but I wanted to dive just really quickly into the history or the etymology of this. Poly means many, nomial means term, so these are many-termed functions. Additionally, you could think of this as the sum of monomials. Monomials are one terms, and so if you were to imagine this is one term, 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 and they've all been added and subtracted together. So you know that monomial means one term, binomial would mean 2 terms, trinomial would mean 3 terms, and generally anything over 3 terms we just call it a polynomial with however many terms it has. For example, with 6 terms. That's what this polynomial is. So we need to be able to tell at a glance if we're working with a polynomial or if we're working with something else. And I'd like you to pause the video right now, take a look at these 6, which you've already printed out the notes so you can see them better than mine here, and decide, hey, which of these are and which of these are not polynomials. So then unpause the video and come back and we will discuss them in just a minute. Hopefully you've paused and you know that this is a polynomial. It is not in standard form, because if it were, it would be in descending exponent order. So it would be x to the fifth followed by 2x cubed followed by negative 4x squared plus 5. You have to make sure that all the exponents are going down in the appropriate order. So 5, 3, 2, and then 0. It is a fifth degree polynomial with 4 terms. With 4 terms. This is not a polynomial because the square root can be thought of as x to the 1/2, and the definition is these numbers here, to be polynomial, have to be 0 or greater and can't be fractions. So that takes all my roots out. This is not a polynomial because I can't have negative exponents. Negative exponents mean something's in the wrong place, so that's not a polynomial. The 3 remaining are polynomials. For D, to figure out the degree of the polynomial, you can imagine having to go ahead and do the foiling. So don't forget that 2 copies of x plus 2 looks like this. And when you're done doing this polynomial, the highest x is going to be an x squared because it's x times x. I don't need to do the rest of this anymore, and these are no longer equal signs because they're just me doing some mental math. That negative 3x squared times x squared is going to be a highest degree of negative 3x to the 4th, so this is a degree 4. You are welcome to either take this out of factored form, because this is in factored form, by doing all of the work and then figuring out which is the highest degree, or do some mental math on it to figure out what the highest degree is. I'll hit the F next because it's closer. You can think of this as negative 2x to the 0, so this is a degree 0, also called a monomial. So one-termed degree 0 monomial. E is a polynomial. It is a 4th degree polynomial. But I actually think we know a word that's better for this. It's a binomial because it has 2 terms. And then it's not in standard form. If I were to put this in standard form, it would be 4x to the 4th plus 5x squared. That is standard form. But if I were to put this in factored form, it would be x squared times 4x squared plus 5. In general, if it's easy to factor, I'm going to ask you to factor it. If it's hard to factor, I'm going to give it to you in factored form. You need to know how to operate stuff when it's in factored form and when it's not in factored form. Moving on here. So we need to talk about monomials a little bit. Let me quickly center this on the page. So I'm going to go ahead and zoom in just a bit. A power function are all the monomials we were talking about before. A power function is a one-term polynomial. So I will give you some examples of power functions right here. X squared, x to the 4th, x to the 6th, x to the 3rd, x to the 5th, x to the 7th. They're all monomials. But here are some more monomials. Negative 7, x to the 41st. That's a one-term polynomial. And it can have numbers in front or it can't. Let's see, g of a t equals 1/2 t to the 4th. That's another monomial. So it's just one term. So I've graphed 3 even monomials and 3 odd monomials. And I'm going to ask you, do they share the same shape? If you can see at the bottom of this piece of paper, it has a lot of different information on it. And so we're going to be answering those questions just briefly here. The first is, it should come no shock that this is x squared, this is x to the 4th, and this is x to the 6th. And if you need to, open up Desmos, right side by side the video, and confirm that. And then these are called even-powered functions, and they do share the same shape. We call this parabola or parabolic. There's two different types of parabolic. Either you have it in its position as the parent function, or you've reflected it over the x-axis. So when I talk about something being parabolic, either I'm talking about this, or I'm talking about it having been flipped over the x-axis. And that's important because if all monomials that have even degree share the same shape, later on when I'm looking at different types of polynomials, you can say, okay, look, I don't care what's going on in the middle here. I only care what's going on the outside. And if it's a parabola, then both of the sides of this go to the same direction. This odd function, we think they have the chair shape. Although I'm telling you, the chair shape is kind of weird, but whatever. And in the chair shape, you're going to see it kind of looking like this shape right here, or you have reflected this over the x-axis and it's no longer starting out that way. It looks like this. What I like about the chair function, though, is that it, as x is going to negative infinity, these are my x's going to negative infinity, I'm going left, the function goes down. My f of x's go down. As x travels to the right, my f of x's go up, which is kind of positive infinity. Unlike the parabola, where in both directions you're going to the same positive infinity, or you're going to negative infinity if it was opening down. These chair functions go to opposite infinities, which I think is fun. But going back to the even-powered functions here, do they share any points? Why, yes. All even-powered functions share -1, 1 when they're in their parent form, and then 0, 0, and then 1, 1. And so I'll put these on here, 1, 1, -1, +1. They're called even functions. They're not odd or neither because they are symmetric to the y-axis. That's the definition. And just a quick reminder from the first week of class, you put a negative x in and you got the original function out. Okay? That's the definition of even. That's exactly what's happening in the parabola. The domain of all of the even-powered is all reals, but the range is 0 to positive infinity. The next piece of these questions is written in math notation that we kind of barely scratch the surface on. So let's take this out. This says as x travels to negative infinity, I want you to think of that as going left. What is f of x doing? And as x travels to the right, what is f of x doing? And this last one here is as x travels to 0, what is f of x doing? Reminding ourselves we're only looking at the even-powered functions. So let's take a look. As x travels to the right, f of x is going up. Saying f of x is going up is exactly the same as saying f of x is going to infinity. As x is traveling to the left, that's going this direction, the y values are going up or positive infinity. But if I'm traveling towards 0, I'm coming at it from both these directions, it looks like my y value here is going to be 0. And that makes sense because at the x value 0, the y value is 0. Okay, let's consider all of this now for the odd chair function. And the easiest way I can do that is to fold the paper. So bear with me while I fold the paper so that you can see the questions and the graph in the same space. Okay. So this is comparing the odd functions. Comparing the odd chair functions, if you take a look at them, you have the shape that it's going down on one side and up on the other, and I just talked about it being opposite infinities, but the question is, do they share the same shape? We've already answered that. Yep. If it's odd, if it's an odd monomial, if it's an odd power function, you're going to have kind of a chair going on in the end. Do they share any points? Yep. The points that they share are -1, -1, 0, 0, and 1, 1. Those are all the ordered pairs that all the odd power functions share, and I'll put those on the graph. Okay. Are these functions symmetric? Well, yeah, they're symmetric to the origin, not the y-axis or the x-axis. They are odd functions, reminding you that the definition of odd was you put a negative x in and you get a negative y out. So don't forget that we have this from the beginning of the class. And then it says, what is the domain? Well, I love odd-powered functions for this because the domain is all reals and so is the range. So everything works in them. And then it asks, what happens to the graph as x goes to left, x goes right, and x goes to 0? So let's take those as three different ideas. As x goes to the left, that's going this way on the graph, going left. The y values are going down. So you say f of x is going to -infinity. As x is going to the right, f of x is going up. So going to the right is this way, and the graph is going up. Last but not least, as x goes towards 0, I start here and kind of zoom in, and f of x goes towards 0. All right. I'll be right back. I'm going to pause so these videos aren't so long, and this will just be part 1.